So by now you should have downloaded this sheet and printed it off, and you should have your pack of cards, and you should have spent some time already either playing this with a partner or just playing it by yourself, which is just a simple game of Snap. And then if you've done activity 2 as well, you should have thought about all the steps that need to take place when you play the game of Snap, because that is how you start to solve the problem. So I'm going to do this myself, because sometimes it's easier to watch someone else do this rather than just follow some instructions on a website. So I'm going to show you how I would do this, and this is using decomposition and abstraction at the same time. So what I've really got to start thinking about is the steps that a computer would need to take in order to program Snap. So I've got my cards. I know that I need a pack of cards. So that's going to be my first thing on my list. So I need a pack of cards. I also know I could draw this as a diagram or something like that if I want to as well. So just leave it like that. It needs to be, especially if I've just played the game, I also know it needs to be shuffled, because that's usually what you do next. So I could put shuffle the pack. Okay, I'm just going to leave that as it is for now. Then I think about the next step. So if I'm just playing Snap and I'm playing with just one other person, I might split the pack like that. I might do it like that, which obviously takes a lot longer to do. Okay, so what I'm going to do, because it's faster, I'm just going to use my eye to split it in half. But computers are really clever, because they can just, once they know they've got a pack of cards and how many are in there, you can just put a formula in there to split it in half equally if you wanted to. So now I'm going to write split pack. So in my abstraction at that point, I might just draw something like that, because I'm just trying to simplify the processes that are happening. And again, you could do this list over here first, or you could do that bit first, or do it together like I do. So that's basically setting up the game. So I've got a pack of cards, I've shuffled the cards, and I've split the pack as well. So now I have to actually play the game. So this is where we need to start thinking. So I'm going to make sure this one goes first. So I'm going to pick this one as player 1. So I know I need a player 1 and I need a player 2. So I could put P1 there, P2 there, 2 players, 1 and 2. These are just notes, okay? They will change as we go along. So I've got my player 1 and a player 2, and I know that player 1, most likely and obviously, is going to go first. So player 1, if we break this down into really small steps, player 1 is going to go like that, okay? Which is really, really easy to do in the real world. Taking a card from here and placing it there. So this is when you start to think, right, well, how are you going to do that on a computer? So I've got to pick a card, I've got to place it on the table, and I now need to know what that card is. So that's lots of steps. So P1, pick first card, put on table. So at this point, I'm starting to think, well, I'm going to need a table as well in my programming. So maybe I would have here a table like that. and then maybe just put one card. Okay, and I think I've covered all of that, but I can come back to it later. Then player 2 goes and player 2 puts it down. So this is a repetition now, because player 1 has done something and player 2 needs to do exactly the same thing but with their cards. So there's a bit of repetition. You can start to spot a little pattern there, and pattern repetition is recognition is down in this area here. So you might put, so it says, are there any patterns? Would you need to repeat anything? So at this point I can start going, both put cards down, because that's just my thinking. I'm computationally thinking my way through this problem. Okay, so next one, player 2, pick first card, put on table. So that happens for both players. So when I'm abstracting this and I'm simplifying it, I shouldn't need to write that whole bit of code again, because I just need to change player 1 to player 2. Okay, then it all just repeats. Oh, so now we've got a snap happening. So it all just repeats, and it repeats until something happens. So again, I need to think, well, it repeats until snap. Okay, now I could have drawn a loop, I could have done whatever I want. This is just my planning. I can tidy this up later on. So it repeats until there's a snap. So how do I know there's a snap? Well, the top 2 cards on the table match. Okay, so every time I put a new card down, I'm going to have to ask, do they match? So, do top cards match? Then you can start thinking about your selection. So at this point we know they're a snap, but player 1 and player 2 can now say snap. So we've got to think about, well, what would happen next in this situation? Break it down into tiny little chunks. So you've got your snap. So if this card is equal to this card, then snap. Then you've got to think, well, how am I going to allow a player to actually say snap? That's a tricky one, that is. This is where your knowledge of true and false is going to help you in this situation. So before anybody's ever snapped, we have got 2 players playing a game, and before any snap has happened, both players, they haven't said snap. So a player can either say snap or they can not say snap. So we can relate that a little bit to true and false. So if you think about it, snap is either true or false for each player. So this is where you start thinking about your variables that you might need to use in this solution. So I might have something like player 1 snap equals false and player 2 snap equals false, and then something that checks if they're true, possibly. And this is where your problem solving goes off into completely different directions. Nobody solves the problem exactly the same way. So this is just where I'm thinking at the moment. So I'm going to have, and this is what I mean by it'll get a mess, your piece of paper will get a mess because things will change, because I know now that I'm going to need to have some kind of variable. So I'm going to have P1 snap false and P2 snap false at the beginning. I'm going to set that to false at the beginning, so that when I'm looking at this repeat loop and it checks if it's a snap, so do the top cards match? If the answer is yes, oh, I'm totally running out of room. I'm going to just do it on the back. Do the cards match? And then I've got yes, and I've got no. So if it's no, I know I've got to keep asking that question. But if it's yes, then I've got this P1 is false, P2 is false. Okay, so what I can do now is I can check whether anybody has said snap. So it's going to have to wait until somebody says snap. Or it's going to have to give them some time to do that, because we don't want it to wait too long, or else it's going to be hard to play the actual game. So maybe wait 3 seconds. So, or we could count something. So 4, 3 seconds, maybe. Is P, name did I use? P1 snap equal to true, or P2 snap equal to true? And then if P1 snap is equal to true, then P1 snap wins, else if P1 snap equals to true, then P2 snap wins, else move on. Okay, now again, this is just my thinking. When I come to actually program this on the computer, it could be wrong, the algorithm might not be perfect, and that's why we've got this area of our sheet to help us think about, well, what's gone wrong. And when you actually start implementing your solution, you will find things that aren't quite right. So this is just my thinking, and it's about just being confident to keep going, even though it starts to get a bit puzzling, which is what's happening to me now. So do the cards match? Yes. So if they do, I'm going to probably give them some time. I want to see if they say snap, and whichever one says snap first, they win the snap, and then we move on. So I'm getting the steps there, but they're probably not quite right at this point in time, but that's okay. That is totally okay. So I'm going to move on then to, so snap, I'm just going to put snap question mark there, because when I get a snap, I then get even more complicated things. So I know I've got a pile here that is building up on the table, and if player 2 had won, then if they'd said snap first, then all these cards now belong to player 2. So I've got some cards on the table, and then the table, the cards need to move from this table to this pack, and it's usually the bottom of the pack. So again, it's easy to do that in the real world, but how on earth do you get a computer to do it? Okay, so now I'm thinking, well, I've got the contents of a table, so move on. So they've snapped. So I'm going to just draw some arrows here, because if player 1 win snap, and if player 2 snaps, they've got to have that pile. So move table to winning player. That's all I'm going to write for now, because I just, you know, at the moment I don't really know what I'm doing with my variables and things like that. So I'm just going to say move table to winning player. This is all part of it. You can't expect to get this right first time, okay? Programmers that have been doing this for years and years and years still find complex problems difficult to solve, and that's the whole fun of it, really. It's getting it right in the end. So I've moved that to the winning player. So now the game just carries on. So game played just starts all over again. So gameplay carries on. And it all just repeats. So we found another pattern now. So both cards put down. Winning cards is going to be a pattern. And then starting again is going to be a pattern, because we'll have already programmed that up here. We just need to get that to start again. So then it'll just carry on. And then at that point, if we've managed to repeat things and get our pattern recognition right, and we've managed to get them, then it'll just keep going. And it'll keep going until it runs out of cards. Now, if we don't put any code there for that situation, then probably the code is going to break, okay? At this point in time, just me rushing through, I now know player 1 has lost, because player 1 has no cards left, okay? So what we also need to check in our program is, well, what do I do now? How do I find out if somebody's won or lost? So as well as checking if these cards have matched each time, we're going to have to check if somebody's got cards left every time. So, do the cards match? So another question that I'm going to have to ask is, do the cards, this is what I mean by you'll get a complete mess. So do the cards match? Do the players have cards left is another question that we're going to have to find the answer to. And then it's just a simple bit of selection again, isn't it? So if player 1, so if the answer is yes there, then we continue to play. Whee! All the way up here. But if the answer is no, then we need to find out who has cards left. They are the winner. Okay? So, I've done a little bit of abstraction as I've gone along. I've done a little bit of pattern recognition, and I've done a little bit of decomposition. I'm still not quite at the algorithm stage, because I've got all these notes all over the place, and the algorithm should be the list of instructions that are required to solve the problem, and they should be very specific instructions. And at the moment my instructions aren't specific because they're all over the place, but I have used those skills of decomposition, breaking the problem down, and abstraction, which is simplifying things, looking for variables, looking for things that can be repeated, drawing diagrams to help me to simplify the issue, so I'm not just writing tons and tons of things out. It could be abstracted a lot more, and the more I abstract this, the more I simplify it, the more it'll start to look like an algorithm. Okay? But that is just me trying to show you what it's like to solve a problem.